Hello everyone, welcome to our next lecture. It is a rainy Friday morning here in Dayton. So hopefully, even though it's cloudy and dark, we have enough light to see okay. All right, let's get started. So today is lecture number 22. We are kind of on chapter 12. The book doesn't really go over the kind of stuff that I'm going over, which I think is a pretty big oversight. At least doesn't go over it in the same way that I do. So no pages in the book to look at to correspond to this, but for next class, do read 3:11 to 3:15. Homework, we're going to figure out what's going on with that this weekend, hopefully, and let you know. And today we're going to cover the topic of conservation of angular momentum. Okay. So at the end of last class, we saw that we could calculate the angular momentum of a particle moving linearly through space, right? So if we put a coordinate system somewhere in space and a particle is flying around, that particle has some momentum. We take the position vector that points from the origin to that vector, or excuse me, the position vector from the origin to that particle with that momentum, and then we can calculate the angular momentum like that. So at first it might seem strange that we're doing this at all because this is something that changes with time and we already have linear momentum. What's the point of having this other quantity, the angular momentum? And the reason that we have angular momentum is that not all systems are linear, of course. The whole topic of this section of the class has been on rotations. So we're interested in objects that rotate, right, or spin or move in some rotational way, like an orbit or something like that. So let's look at angular momentum for those types of systems, and we'll see, of course, that it's a much more useful quantity than if we just have something flying through space. So let's take the example of a single particle, and it's going to be executing some orbit right around the origin. So this particle has some mass m, it has some instantaneous velocity v, right? This is some tangent to this symmetric orbit that's following. If it's not clear that this is the way it's supposed to be, this should be at the center of this orbit, right? Again, I'm not very good at drawing. And we have some r vector that points to that particle. And of course, that r vector and that v vector are going to change with time. But we'll see how we get a simplification for angular momentum in the case of this orbit. So we have r cross p for our definition of angular momentum. And now we just plug in our definition of linear momentum. That mass, that m, goes through the cross product because it's a scalar. The cross product doesn't talk to it, it only talks to vectors. And then when we carry out that cross product, we see that, we can take this r vector and this v vector, right? When we cross them, r cross v, right? That r vector and that v vector are always perpendicular, right? That r vector and that v vector, they're always perpendicular, even though they both change as we go around this orbit. They're the same with respect to each other. And that means that when we take the cross product, we're going to get the magnitude of the position vector, the magnitude of the velocity vector, times the sine of the angle between them, which is pi over 2, times the unit vector that points in the direction defined by my cross product, right? If I have r is pointing in the xy plane, and v always pointing in the xy plane, and they're always perpendicular, well, my r cross v, So if I took the vector as I had it drawn here, this r vector would be completely along y, this v vector would be completely along x. I would go x cross y, I would get z pointing in this direction. Right? So I have my z hat vector, and that's the direction that my angular momentum points in. Now, this simplifies because sine of pi over 2 is just 1, so I have m r v z hat. Okay? I drew my coordinate system a little bit differently than I normally do. Right? You see x, y, z. I can write it this way too, as long as all my cross products are defined the same way, right? This is that same coordinate system except just rotated, right? So if I grab it and rotate it that way, it'll be the other coordinate system that perhaps you're more familiar with. Okay. The next thing we do is we take this v and we want to continue defining things in terms of their angular quantities. So we know that there's a relationship between the linear velocity and the angular velocity, which is that linear velocity, or rather tangential velocity, to be completely specific, is equal to angular velocity times the position vector, or the radius, right, pointing to the object that's under rotation. So we just sub that in, and we get m r squared omega z hat. Now, what we're going to do is we're going to subsume this z hat into this omega and promote that omega to a vector, right? So before this was just the magnitude of the angular rotation, right? Radians per second. Now this is still radians per second, but that rotation points in some direction as defined by the right-hand rule. So this object is going around this orbit. So we're curling our fingers in the direction of that orbit, in the direction of the rotation, and of course we get our thumb pointing in the z direction. So this angular velocity vector points in the z direction. Right. So this mr squared, that should seem very familiar. It's the moment of inertia of a single particle orbiting symmetrically, which is exactly the situation we have here. So we get a much more useful and intuitive expression for the angular momentum as I omega. So this equation, which holds only for rotationally symmetric systems, tells us that the angular momentum is equal to the moment of inertia times angular velocity. Our definition of linear momentum is mass times velocity. So again, we see that we have the same sort of structure when we're talking about angular systems and linear systems, that if we take the more familiar linear system and just sub in, right, the angular things, we get the same equation for the angular system. So we take out linear velocity, we plug in angular velocity, we take out mass, we plug in moment of inertia, which is what we have in angular systems instead of mass. And then we take out velocity, we plug in angular velocity. So the equations have the same sort of structure, right? And again, this comes with the proviso that it only works, this equation is only true when we have a rotationally symmetric system like that. Otherwise, we run into complications. Oh, that's not a blank page. No, these are blank pages. Okay, there we go. Hold on, I'm gonna get a little more paper. Pause. Okay, I've gotten some more paper. So to demonstrate that the fact that we run into problems if not everything's not symmetric, let's imagine we shift the point of origin of our coordinate system along the z-axis. So we're going to take this guy and we're going to shift the coordinate system up, actually, right? But this object is going to stay in that same position in its rotation. So here's our coordinate system, right, which we have shifted up. So the particle is actually rotating down here somewhere. So here's that particle of some mass m, its tangential velocity vector. But now the problem is that this position vector, right, I'm just going to, sorry, that doesn't look good. I should have planned it out. I'll write this down here now. So a velocity vector is still going to be tangent to this orbit, but now the position vector has changed. So we're going to move this velocity vector over here. I remember I can grab vectors and just move them around. And now, when I calculate my angular momentum, when I calculate that r cross p, or r cross v, right, I'm going to have r, this is difficult to do, the way I have it drawn. Yeah, so I have r, oh god. Here we go, r cross v, so that angular momentum vector is going to be pointing off into the background, right? It's the way I have it drawn, it's going to be pointing off sort of more aligned along the negative x-axis. So it's not pointing in the z-axis anymore. It's pointing that way, right? In this r cross v, oh, that's a better way to do it. R cross v direction. It's going that way instead of up, instead of that way. So it's been tilted from its position along the z-axis. So that L equals I omega holds only for systems which are symmetric about the axis of rotation, right? That have their center of mass on the axis of rotation. So if I have a system where I have two particles following a symmetric orbit, right? This is a symmetric system. I can see clearly that the center of mass is right there. Okay, and that means that my L equals I omega equation is going to work fine here. Also, I could imagine I have a disk, right, a solid object rotating around. And as long as I have this axis of rotation through the center of mass, through the center of symmetry, this is all going to work out fine. But if I have something that looks like this, right, where I have an object rotating like this, and I have my origin shifted off from that center of symmetry, well then that L equals I omega doesn't work anymore. So we just have to be a little careful when we apply, excuse me, this equation. But it'll be clear most of the time when we can and can't use it. All right, so let's return to our definition of torque so we can continue to build up the mechanics we need to understand rotating systems. So when we derived our linear momentum, we saw that the thing that changed linear momentum was force, and that gave us an alternate definition of our Newton's second law. So in other words, we saw that force was equal to dp dt, right? Force is the thing that changes momentum. So now we're going to do something very similar for torque and angular momentum. So we'll start with our definition of torque that we have now with our cross product, R cross F. And now we're going to consider this for a net torque. So not just one torque, but many torques added up with one little simplification. So we're going to add up each individual torque from each individual force, and that's going to give us our net torque. Okay? The thing that's the simplification here is that I have all of these R's the same. So all of these forces are being applied at the same point on this object or on this system. Now, if we have an object, and this is a really important point, and causes people to get lots of questions wrong, so remember what I'm about to say. If I have forces that are applied at different positions, these R's are not going to be the same. And this means that would mean that the next step of the calculation that I'm about to do would be different. Okay? If I have, I'll just do the next step and then we can see the difference. So if we have R cross F1 plus F2, et cetera, et cetera, et cetera. Right? If each of these forces is applied at a different point, each of these R's is going to be different. Therefore, I won't be able to bring this one R out front. Okay, so when we have different forces being applied to an object at different points, we have to calculate each individual torque and then add them up. So the more general version of this would be torque net equals R1 cross F1 plus R2 cross F2 out to however many there are. Okay, but we're going to take a simplification here. So we have R cross sum J Fj equals R cross F net. Okay. Now we have our Newton's second law up here, which I should have written a net in there also. And then I'll just write it again just for fun. F net equals dp/dt. So likewise, torque net equals R cross dp/dt, right, which we get just from here. So I'm going to put a little star next to this because we need that equation again in a second. Now we're also going to look at the angular momentum, because right now this is an equation that's between the torque and linear momentum, and of course we want the angular momentum, so we're going to change that by applying our definition of the angular momentum of R cross P. And now what we're going to do is, because we want something that looks like this, so we can plug in our angular momentum into there, we're going to take the derivative of both sides of this equation with respect to time. So dl dt equals ddt R cross P. And now if you go back and look at your rules for taking the derivative of something that's under a cross product, you'll see that we get dr dt cross P plus R cross dp dt. Right, we take our product rule, but now we're just being very careful that since we have our cross product as the product, that these things have to stay in the same order that they're here. So R and P and R and P. Okay. So now we're going to look at this term here, just individually. So this calculation is slightly subtle, so it's good to pay careful attention. So we have this dr dt cross P. Okay. The change of the position vector with respect to time is just the velocity. So we have v cross P from a definition of velocity, and then we're going to plug in our definition of momentum, so that you have v cross m v. Again, that m can come out front. We have v cross v, which is equal to 0. Right? Again, taking the cross product is asking the question, how perpendicular are two vectors, and two vectors that are the same are as not perpendicular as they can get, so we get 0, right? The cross product of two vectors that are the same is always 0. So this term here is 0. So now we need to look at this term here. But that is available, where did I put it? Oh, from over here. No. Ah, yeah, here it is. From our start equation, right? R cross dp dt, that's just the torque. So we have d L dt equals torque net. So now this gives us our Newton's second law for rotating systems which are subject to some external torque. So this is similar in form, excuse me, to our Newton's second law for linear systems, where we had F net equals dp dt, and we have torque net equals dl dt. So as force is the thing that changes momentum in linear systems, torque is the thing that changes angular momentum in rotational systems. So this is an alternate form of Newton's second for rotational systems. Oh, there's a staple there. Okay. I'm going to slice my hand open on this. If I leave it there, I know it. Okay. There we go. So again, torque net dl dt. Okay, now we have what we called our alternate form of Newton's second law. Now we want to derive the original form, right? We want something that looks like F equals ma. So we just sub in our relationship between angular velocity and angular momentum. That derivative goes through the constant moment of inertia, and of course, the time derivative of the angular velocity is just the angular acceleration. So we have torque net equal to y alpha. So this is like our F equals ma. Right. So if I wanted to write this in exactly the correct way with all of the subscripts, I'd have torque net external equals dl of the system dt. So if I have some system, some composite system that's made up of many different objects interacting, and I don't know what I'm drawing actually. Imagine I have, I don't know, some gears in this thing, right? Everything's, I don't know what this is. This is maybe a clock or something where I have some complicated mechanics going on in there. This is what the inside of machines look like, right? So I have, imagine I take a clock, right? A giant grandfather clock with lots of internal moving parts, and I want to rotate it, right? Maybe it's facing the wrong direction. I want to turn it to face a better direction. When I want to turn that object, in other words, change its angular momentum from 0 to some positive number, all the internal mechanics of that clock don't matter, right? The thing can be humming and whirring and doing whatever it does.